Hi students. So today I will discuss electric dipole, which is a topic from electrostatics, right. So in this video we will discuss complete details regarding the electric dipole, right. So let us see what is mean by this electric dipole, right. So here electric potential, electric field. So these all are the topics I already discussed in my previous videos. If you did not watch, please watch that video so that you can understand very clearly. Now tell me what is meant by electric dipole. Most of the students know, right? If I ask what is this electric dipole, so they answer that two equal and opposite charges, therefore this is minus q and therefore here it is plus q. So minus q and plus q, equal and opposite in magnitude. Magnitude is same, opposite in polarity now, right. So equal and opposite charges now separated by one small distance, we will call it as like a electric dipole. This you might have studied now. See, if I keep it like this, why they will not attract? Why they will not become like a neutralize onto this? Clear? So therefore electric dipole is not this definition, no. So electric dipole is nothing but one molecule or a atom. So is nothing but a neutral atom or neutral molecule, no, is nothing but a electric dipole. How? Let us see here. Therefore here there is a you can take it as atom here, no. Therefore total positive charge will be at the center, no, and all the electrons, no, so will be revolving around the nucleus now. Therefore how much amount of positive charge is there, that much amount of negative charge will be there in a neutral atom and a neutral molecule. So here therefore total concentration of the negative charges, total concentration of the positive charges, total negative charge of this one, no, and total positive charge, if they are concentrating at one point, no, therefore they are concentrating at one point, they are said to be non-polar molecules. That means does not have like a permanent dipole moment. Suppose here therefore here total negative charge is concentrated at one point, total positive charge is concentrated at another point, no. So therefore it is having like a permanent dipole onto this, right, permanent dipole moment. That is said to be like a polar molecules now, right. So therefore any atom now, like whether it's polar or non-polar, now what will happen now? If you apply the electric field, what will happen now? If you apply the electric field, so this side is positive, this side is negative, all negative charges now will comes to here. This is negative charges now will comes to toward this side. So this all positive charges will be shifted toward this side. That means totally, so what will happen now? Here total negative charge it will be present, here total positive charge it will be present. It is a neutral atom, that means how much positive charge is there, how much negative charge is there now. Therefore it will be the same, but these two are separated by small distance, no. So therefore this molecule is nothing but like a dipole, right. Some molecules will be there whose without any electric field, no, without any electric field, total positive charge and total negative charge is concentrated, it will not act like any dipole onto this one, no. That is said to be like a non-polar molecules. So suppose total without any electric field, if total negative charge is concentrated at one point and positive charges is concentrated at another point, no, small distance is there, no, that is said to be like a polar molecules, no. Clear? So mostly polar molecules like a HCl, water, so that are comes under like a polar molecules, no. Non-polar molecules like they are concentrating, no, like O2, N2, right, like that, no, that will become like a non-polar molecules. Clear? So that means if there is without electric field, if it is like a dipole is there, that is said to be polar. If with electric field, if there is a dipole is there, that is said to be non-polar, right. So now we came to know that what is a dipole means. Dipole is nothing but one molecule. So any molecule which is kept inside the electric field, it will act like a dipole, right. If I remove it, no, then it can come back to the original positions. So now onwards dipole is nothing but not separated by distance, no, it is just nothing but a molecule. That's why this is important onto this, right. So if you want to study about this dipole, so can you tell me what is the total charge on the dipole now? Total net charge on the dipole. Total net charge on the dipole, it will be equal to 0. Why? How much amount of positive charge is there, that much amount of negative charge is there. So this total dipole, no, for this it is having some center onto this. Suppose it is having some center here, no, therefore this is taken as center. So this is slightly certain distance here, no, therefore it is L is a distance from the center. So negative charge is also kept at certain distance, no. So therefore for this dipole we can define it as like one dipole moment. So what is this dipole moment now? Dipole moment. So dipole moment is denoted as, it is P. So it is nothing but a product of charge into the distance between the two charges. Here distance between the two charges is not L here, no. Why we consider from here to here L, here to here L. Distance between the two charges is nothing but a 2L. This 2L is nothing but a distance between the two charges. Be careful onto this. Clear? So this dipole moment, right? So this is a dipole moment. So what is the unit now? It is nothing but a coulomb. Coulomb into meter. What is the dimensional formula? So meter is nothing but L. Coulomb is nothing but AT. Therefore T into A. So this is your dimensional formula. Is a vector or scalar? Therefore it is a vector quantity. So what is the direction now? Direction of your dipole moment is from negative to positive. So what is the direction here now? So direction of your dipole, so dipole moment, it is taken from negative charge to positive charge. Clear? So this dipole moment is a vector quantity. Therefore you have to follow all vector rules to calculate this one, right? So let us see some simple question onto this one. So about this dipole and dipole moment. Later on we go for electric field line due to the dipole. Let us see, therefore here let us see one question now. So one positive charge is there, 10 microcoulomb, positive 10 microcoulomb is located at, so therefore here 0, 0, 4 centimeter. So plus minus 10 microcoulomb, suppose here no, minus 10 microcoulomb, so is located at 0, 0, minus 4 centimeter. Clear? So what will be the dipole moment of this one now? See where it is there now, it is along the z axis now. Suppose I will take it as this is your z axis now. So this is your origin now. So where the charges are located now? Therefore minus 1 now. Therefore here, so minus 10 microcoulomb, where it is located now? Therefore minus 4 centimeter. So here plus 4 centimeter it is there now, plus 4 centimeter plus 10 microcoulomb is here this one. What is the dipole moment? A dipole moment is defined as product of the charge. Charge is how much now? 10 into 10 to the power of minus 6. 10 microcoulomb. Distance between the two charges. What is the distance between the two charges now? Here it is from here to here 4, here to here 4. That means 4 plus 4, total 8. 8 into 10 to the power of minus 2. How much now? 8 into 10 to the power of minus 8 plus 1. Therefore, so 10 to the power of minus 7 coulomb into meter. What is the direction here now? So negative to positive, it is along the z axis now. Therefore, it is nothing but a plus kk. This is your dipole moment of this dipole. Clear? Right? Now let us see one more question here now. One more question you can calculate it now. Suppose there is a one positive charge is there now. Therefore here also some positive charge is there no, right? So here, therefore here negative charge is there. Therefore here negative charge. So minus 2q is there. Therefore here it is L, here it is L. Now we want to calculate total net dipole moment. Net dipole moment here. Clear? So what is the dipole moment here now? Whether the dipoles are there or not? Yes. Here minus 2q is there now. This I can reread it as, therefore here is minus q and minus q. This minus q and plus q, this is here one more dipole here now. Minus q and plus q, one more dipole is there. What is the dipole moment here now? Therefore q into L. So what is the dipole moment here now? Therefore q into L. So how are they now? Therefore they are acting at perpendicular to this one now. So resultant of this one now. Therefore here, so here both are same and perpendicular now. Root 2 into dipole moment of this one now. So therefore root 2 into q into L will be your net dipole moment of this combination. Clear? So like this you can calculate the dipole moment, right? So now let us see one more concept now. So electric field, right? Electric field due to dipole. So we can calculate along the x-axis, along the y-axis, and at any arbitrary point now. So we will take it as like a minus q is a minus q and this is here plus q. So we will take it as from the center now. Therefore here, so this is your dipole moment, it is nothing but this is L and this distance is L. So we want to calculate along certain distance here now. Therefore at a distance is r from the center of your dipole, right? This is along the axis of this one now. Therefore this is nothing but along the axial line. along the axial, right? So electric field along the axial. So I already told so many times, no, therefore if you want to calculate the electric field, there you have to consider plus 1 coulomb. Here, so I should consider plus 1 coulomb, no. This is positive charge, no, will undergo like a repulsion, E due to positive. This negative charge, positive charge, it will undergo like a attraction here, no, E due to negative. So this distance is how much, no, R minus L, and this distance is how much, no, therefore R plus L, clear? So what will be the net one, no? Therefore here Q and Q same, but this is very smaller here, no, that means this side electric field will be larger, that means this electric field is larger, this electric field is smaller, net electric field is along this direction, no? That means, so this side is your dipole and this side it will be your electric field direction. That means electric field along the axial line is along the parallel to the direction of your dipole moment. Now along the axial, so you can write down E due to plus minus E due to minus, clear? So E due to plus is how much now? Therefore here it will be K into Q, KQ by, what is electric field? KQ by R square. What is R now? R minus L whole square minus KQ by R plus L whole square, clear? So now, so we can rewrite it as like a KQ. Therefore you can take it as, therefore here 1 by, therefore you can rewrite it as, simplify this one, no. So R minus L, so whole square into R plus L whole square, clear? So this side it is taken now, therefore R square plus L square plus 2RL, this side A plus B whole square, this side minus. So this minus of whole square means how much now? Minus R square minus L square minus, so that is plus 2R into L. Therefore these two are cancelled onto this, clear? So therefore here electric field along the axial, no, along the axial line we can rewrite it as KQ into 4RL, because 2RL. So by this whole square means A plus B into A minus B, therefore R square minus L square whole square, clear? So therefore here you can rewrite it as again, no. So this 2, therefore here 1 by 4 pi epsilon naught K value into this I can write down 2 into, therefore here 2 into 2, I mean Q into 2L, Q into 2L into R divided by R square minus L square whole square, clear? So what is this one now? Q into 2L is nothing but a dipole moment here, no, right? So we can rewrite it as along the axial line, no, along the axial you can write down 1 by 4 pi epsilon naught into 2 into P into R divided by R square minus L square whole square. Therefore, so electric field is along the direction of your dipole, clear? So that means electric field along the axial line is parallel with a dipole moment, clear? So this is for a far distance, no. So we will take one short dipole. See, atoms are very smaller, no. Always better to go for short dipole only. What is this short dipole? Short dipole means what? What you can remember now? The distance between the two charges, no. Therefore, distance between the two charges is very lesser compared to the distance what we are calculating now. Therefore, that means, so the dipole was very smaller now. That means this is very closer, we are calculating very far away distance. So that is we can condition now, that is L is very smaller than this one now. Therefore L is already a smaller, so therefore what you can write it now? Therefore in this one now L square can be neglected. L square can be neglected. So therefore what you can write it now? E along the axial, it will be can be written as 1 by 4 pi epsilon naught into, therefore 2pr divided by r to the power of 4, because L square removed, whole to the power of 4. Therefore you can cancel it here, no. So therefore it will be r cube. Electric field due to the dipole, so this is very important, no. Electric field, so due to point charge, it is inversely proportional to the square of the distance. Electric field due to the dipole, it is inversely proportional to the cube of the distance. Why electric field is very quickly falling in the dipole now? Electric field is falling very quickly in the dipole. Why? Because inversely proportional to R cube. So in point charge it is lesser now. Why? Because in the dipole no, two equal and opposite charges are there, therefore one positive charge, net charge is going to become to 0. Whatever the field lines are there, it will be taken by the negative charge now. That's why electric field will be falls very quickly in the dipole. That's why it is inversely proportional to the R cube. Clear? So this is these are the points no. So electric field due to the dipole along the axial line, right? So now this point you need to remember no, this formula. So electric field due to the dipole along the axial line no, 1 by 4 pi epsilon naught into 2p by R cube. So similarly, therefore electric field due to the dipole along the equatorial line. Equatorial line. What is this equatorial line now? Let us see this one. No? So this is your minus q. So this is your plus q. This is your center. No, this is L. This is L. Now we want to calculate the electric field at this perpendicular distance onto this. Therefore, this is the axis no perpendicular to this axis. Therefore, at certain distance r, we want to calculate electric field. So I already told so many times no. Therefore, here plus 1 coulomb you have to assume. So this is minus. Therefore, this it will be your due to this one no. So it will be attracted toward the side. Therefore, it will be E due to minus. Correct? So this is a no. Therefore, E due to plus. Clear? What is this distance now? This distance is nothing but a perpendicular. Pythagoras theorem no. R square plus L square. Clear? Right? So here how it is there now? It is acted like this no. So here this field we can electric field no, we can split this one into two components no. So these are the two components due to E plus no. So we can take it as this is right. So we will take it as therefore here we can take it as this angle is theta here no. This also it will become like a theta. So when it is theta here no, therefore here it is the same straight line no, this also theta. So theta means this is E plus cos theta, this is E plus sin theta, correct? So this one also we can split this one no, this one we can split like this, correct? So now so this one no, therefore it will become like a this is theta. Means also this also theta no, therefore this is also theta, therefore it will be E minus cos theta, so therefore E minus sin theta. So here same charge, same distance, electric field plus and minus same no, theta is also same no, along this vertical direction no, electric field will be 0. Why? Because this side E plus sin theta, E minus sin theta. So electric field at equatorial line no, therefore it is nothing but a, so along the equatorial line it is nothing but E plus cos theta, E minus cos theta. E plus and E minus both are same. So therefore 2E minus cos theta. Anything you can take it now, right? 2E minus cos theta. What is E minus now? 2 into E value. E is how much now? K into Q by, so this is no root of R square plus L square whole square means that is nothing but a R square plus L square. Clear? Into cos theta. Cos theta is what you can write now? Cos theta is nothing but a, this distance is L, so adjacent side by hypotenuse. L by adjacent side, this is cos theta. What you can write now? Here L by, so root of R square plus L square. L by root of R square plus L square. Therefore, what you can write it now? Here K into 2QL, it is nothing but a dipole moment divided by, therefore R square plus L square to the power of 3 by 2. This is along the equatorial line. So what is the direction here now? Dipole moment is toward this side. Dipole moment is toward this side, but electric field is toward this side. That means anti-parallel onto this. Clear? So therefore here if you write down in terms of vectors no, so this it will become like a minus 1 onto this. Clear? So electric field due to the dipole along the equatorial line, so you can rewrite it as, so therefore here you can read it as 1 by 4 pi epsilon naught into P by therefore R square plus L square to the power of 3 by 2. So for a short dipole means what? Short dipole, just now I already discussed, no? When distance is lesser than this here distance after this. That distance between the two charges is less compared to the distance here now. So when it is less now, so what will happen now here? So you can remove that, L square can be neglected, no? L square can be neglected. So therefore what you can write now? E along the equatorial line 1 by 4 pi epsilon naught into P by R cube. Clear? Along the equatorial line for a short dipole, along the axial line also we discussed. We can have the relation now. Therefore here E along the axial, so what you got it now? It is nothing but a 2P by R cube. Here P by R cube. That means it is 2 times of along the E equatorial line now. Clear? So this is axial means parallel, no? This is equatorial, anti-parallel onto this. Clear? In this way you can solve the electric field due to the dipole, right, along the equatorial line and along the axial line now. Correct? So now let us see, right? So let us see one more question here, no? One more question here, no? So suppose here we can write it as like one question, no? Therefore here one dipole is there plus or minus 10 microcoulomb, so separated by a distance of 10 centimeter. So we want to calculate therefore E along the axial line, E along the equatorial line at a distance of R is equals to 1 meter. 1 meter is very larger compared to the 10 centimeter, no? Therefore you can take it as like a short dipole now. Clear? So therefore E equatorial line, what you can write it now? First of all, dipole moment. Dipole moment is how much, no? Q. Q is how much now? Q into distance between the two charges. Q is how much now? 10 microcoulomb. 10 into 10 to the power of minus 6. Distance between them is nothing but 10 into 10 to the power of minus 2. So 10, this one get cancelled, 10 to the power of minus 6 coulomb into meter. This is your dipole moment. Clear? Along the equatorial, along the axial line, so what you can write it now? It is a short dipole. Why? Because this distance is very larger compared to this one now. Clear? So 1 by 4 pi epsilon naught value is 9 into 10 to the power of 9 into 2 P. P is how much now? 10 to the power of minus 6 by R cube. R is how much now? 1 cube. How much it will be now? Therefore it is 18 into 10 to the power of 3. 9 minus 3. It is 9 minus 6 is nothing but 3. So therefore Newton per coulomb. This is along the axial. So along the equatorial is how much now? Along the equatorial you can rewrite it as along the equatorial. So exactly half of this, no? That was 9 into 10 to the power of 3 Newton per coulomb. This is here along the equatorial. Clear? Right? So at any general point, no, if you want to calculate it, electric field due to dipole at any general point, no, I want to calculate it now. Clear? Right. So electric field due to dipole at any general point. Listen carefully now. Therefore, this is one short dipole we are going to take it now. This is one dipole, that is nothing but minus q. This is here plus q. Clear? Right? So let us see now. Therefore, here minus q. This is here plus q. So here what we want to calculate now? We want to calculate from the center, no? At certain distances r. We want to calculate now. Here what you can write it now? What is the dipole moment here now? What is the dipole here now? Very very important. Try to understand here now. This side it is your dipoles. Let us take the short dipole only. This is your dipole. This is making an angle theta here now. So what I will do now? I will split this one into two components. Therefore, what is that component now? Therefore, here we can rewrite it as, so one component, no? Therefore, along this direction and along this perpendicular to this. Clear? Huh? So that means this is your dipole moment, this is P. So this one we can split this one into two components. So this is exactly like a perpendicular to this. That means it is along the equatorial line. So this component is how much now? Therefore, P, this is your opposite side, no? Opposite side means sine, okay, this is, no, this is like this. So therefore it is P sine theta. P sine theta. This is p sin theta creating the along the equatorial line. This side is a dipole moment, means this side it will be your electric field due to perpendicular to this, correct, that is equatorial line. So this is along the axial line, therefore it is along this one now, E due to parallel, right, along the equatorial line. What is this one now? P cos theta. Clear? So the resultant of this one is how much now? The resultant of this one, it will be E like this. This is your, you can rewrite it as root of E perpendicular to square and E parallel square. What is E perpendicular now to this one now? E perpendicular, no? Perpendicular means equatorial line, no? What you can write it now? K into P by R cube, that is P is nothing but a P sin theta, correct? So E parallel along the axial line, no? Therefore what you can write it now? K into 2P by 2P sin theta by R cube. Clear? So therefore what will be the electric field at any general point now? Electric field at any general point now. So you can rewrite it as, here you can write down this is Kp by R cube and K, right? So you can take it on to this one, no? Kp by R cube, this can be taken as no common, no? Kp by R cube taken out onto this root of this one. Therefore it will be sin square theta plus, sorry, here this is cos theta, okay. This is cos theta. Therefore here it will nothing but a 4 cos square theta. Clear? Correct? So here in this one now I can take it as 1 cos square theta, remaining things, no? So E is equals to K into P by R cube. So root of sin square theta plus 1 cos square theta is nothing but 1 plus 3 cos square theta. Clear? 3 cos square theta. This is your electric field at any general point. Understood? Right. So what is the angle now which is made with this one now? What is the angle here now? Therefore this is your alpha. So therefore tan alpha, what you can write it now? Tan alpha is nothing but a E perpendicular divided by E parallel. E perpendicular is how much now? This one, no? E parallel is nothing but a this one, no? Therefore 1 by 2. Therefore tan theta, therefore this is nothing but a tan alpha. So this is your direction, no? Therefore electric field with the position vector onto this, right? So this is your general point, no? Suppose if you want to calculate along the axial line, no? Theta is equals to 0, substitute it, no? Theta is equals to 0, cos 0 is 1, no? So 3 plus 1, 4, therefore 4 root is nothing but a 2 Kp by R cube. So along this one, no? Equatorial line onto this, therefore theta is equals to 90, cos 90 is 0, so therefore Kp by R cube. Clear? In this way you can solve the problems of our electric dipole at any general notation on this. Clear? So very important concept, no? So please go through this one. Clear, students? Now we will discuss regarding the potential due to electric dipole, right? So potential due to electric dipole, right? So potential formula already we know it, no? What is the potential formula? Therefore K Q by R, it is a scalar quantity, no need to take any directions onto this one. Clear? So let us see here, no? There is a dipole is there, no? This is 1 minus Q and therefore it will be the plus Q. Clear? So from the center, no? So we want to calculate the potential at a distance, no? This distance is L, no? So at a distance of from the center to the dipole. So at this point we want to calculate the potential along the axial onto this, right? So here therefore here potential, no need to take any directions onto this one, no? Directly due to this one now, therefore this is nothing but a R minus L. So this distance is nothing but a R plus L. Clear? So potential at this point now, potential at along the axial now, it is because of potential due to the positive and plus potential due to the negative, right? So potential due to along the axial one now, the potential due to positive charge is how much now? K Q by therefore R minus L. So therefore plus K into minus Q by therefore R plus L. Clear? Why? So it is negative charge, no, negative potential here now. So we can rewrite it as potential. So KQ, we can take it common now, 1 by R minus L. So minus 1 by R plus L. So we can simplify it, no. Therefore potential along the axial, no. So KQ, so you can take it as R plus L minus R minus of minus plus L divided by R plus into R minus L, therefore R square minus L square. Clear? So minus R plus R get cancel out, no. Therefore along the axial, no, K into Q into 2L divided by R square minus L square. Right? So Q into 2L is nothing but a dipole moment Kp by R square minus L square. This is your potential due to the dipole, right, along the axial line. But for a short dipole, short dipole means what is what we discussed, no? For a short dipole, what you can write it, no? So L is very, very smaller than this radius onto this. Therefore L square can be neglected onto this one, no? Potential due to the dipole is nothing but a Kp by R square, therefore 1 by 4 pi epsilon naught into P by R square. So this is potential due to the dipole. One interesting point here, no, potential due to the point charge. What is the potential due to the point charge, no? So potential due to the point charge, it is inversely proportional. See, potential due to this point charge, no, so it is inversely proportional to the distance due to the point charge, no. So therefore due to the dipole, you can see it, no, potential due to this dipole, no, therefore so it is inversely proportional to the square of the distance. So that means potential is falling very, very quickly in the dipole. Why? Because again the total negative charge, total charge in the dipole, no, it will be the 0. So due to minus charge and positive charge, no, therefore net charge is getting falling quickly. So that's why the potential also will be falls very, very quickly now, right? So this is a very, very important point. So potential due to the dipole is inversely proportional to the square of the distance. So this is along the axial onto this one, no. Therefore potential due to the dipole along the equatorial line, due to the dipole. So this is your minus Q, therefore here it will be the plus Q. So therefore we can rewrite it as one interesting point, you can write it, no, here along the equatorial line, no, this is along the equatorial line, right. So here it is same distance, no, same charge, therefore potential at this point is 0. So if you take at this point, no, therefore same distance here, no, and also same distance here, no, same charge, same distance and onto this one, no. So here also because of due to positive charge, negative charge, no, both it will become nullified onto this. Therefore along this complete equatorial line, no, therefore potential will be equal to 0. There is no potential along the equatorial line, right. So along the axial line, so Kp by R square. So but along the equatorial line, so it is nothing but a potential will be 0 due to the dipole onto this, right. So now we will see. So at certain distance, you know, at certain at general point, no, therefore here V due to dipole at any general point. So this also last time we derived, no, therefore exactly we can derive same way, therefore this is minus Q, so therefore it will be the plus Q, therefore this is at the center, no. So here along this direction, no, therefore at certain distance R we want to make it like theta. Why? Because this side is a dipole moment, no, this is your position vector. Here we want to calculate the potential at this point, no, at any general point. Here also like last time we discussed, no, this is your dipole, moment, no. What I will do now, this dipole moment I will split into two parts. What are these two parts? No, therefore this part is nothing but a, so P cos theta, and this part is nothing but a, so P sin theta. So this P sin theta is nothing but perpendicular to this one, no, therefore along this direction, no, therefore potential due to the perpendicular it will be the 0, just now we discussed. along the equatorial line. If this peak sin theta is nothing but it's 0 here now. Clear? Therefore, here along this direction, no, so because of due to this p cos theta, so therefore potential along this direction, no, k into p cos theta by therefore r square. Clear? So therefore here along this direction therefore potential was 0, along this one, no, potential will be so kp cos theta by r square. So at any general point, no, what we got it now, what you got it now, so kp by k value is nothing but 1 by 4 pi epsilon naught into p cos theta by r square. This is your potential due to the dipole along any arbitrary point. Clear? So if theta is equals to 0, cos 0 is 1, so kp by r square. Therefore if it is along the equatorial line, so theta is equal to 90, cos 90 is 0. Therefore along the equatorial line, so potential will be 0, along the axial line kp by r square. Clear? So potential is a vector, I mean it's a scalar quantity, but dipole moment is a vector quantity. So therefore what you can write it now, therefore 1 by 4 pi epsilon naught. So you can write it as 1 I cap onto this. So p dot r cap by r square, so will be your so vector form of our potential due to the dipole. Clear? So if you know the vector, no, r vector by r cube, you can write down any general point, no, therefore 1 by 4 pi epsilon naught into p vector dot r vector by r cube. So this is your potential due to the dipole at any general point. Clear? So very important concept, no, so try to go through it thoroughly, right? Now we calculated the potential and electric field. Now we will see if you keep the dipole in the electric field, what will happen now, right? So let us see now. Therefore here, so dipole in electric field. Suppose I will take it as first of all uniform electric field. So I will take it as uniform electric field. Uniform electric field means what? Always everywhere, no, electric field will be same here. No. This is your electric field. This side is positive, this side is negative. Now I will keep a dipole here now. Therefore what is the dipole here now? Therefore it is minus q. I will keep it, no. So therefore it will be plus q. That means one atom molecule is kept in the electric field. What will happen now? So this is positive charge. What it will do now? It will be, I mean, positive electric field. Therefore everywhere, here, everywhere the electric field will be the same. So this side it will be going to experience a force, no. F is equals to q times of your E. So due to this one, no, therefore this is repulsion, attraction, no, it is going to experience a force, no. F is equals to q times of your E. So therefore at this point and at this point, therefore at this point and at this point, electric field will be same only. Understand, no? Electric field is same, means this side force is same, this side force is same, no. So what will be the net force acting on the dipole now? So therefore net force. So net force acting on a dipole is 0. That means there is no force acting on this dipole. The dipole will not displace, will not translate now. Therefore if a dipole is kept in a uniform electric field, so there is no translatory motion. Why? Because there is no translatory motion. Clear? No translatory motion. Why? Because net force is equal to 0. But what about the torque now? Net torque will not be equal to 0. Why? Because this side, this is what it is doing now. It is making to rotate like this. This side it is making to rotate like this. That means this is making to rotate like this. So this also making to rotate like this. That means, so both the torques are acting in the same direction. No? Net torque will not be 0 onto this. Therefore, so net torque will not be equal to 0. So therefore it will undergo like a rotational motion. You understand, no? So therefore it will not go in the translatory, but it will undergo like a rotational motion. So there is a torque is going to act now. What is the torque acting on this one? Torque is nothing but a force into perpendicular distance. So about this torque and system of particles, no, I already uploaded one video. So please go through it thoroughly about the torque, angular momentum and everything detailedly I discussed, no. Please go through it. So I'll keep it in iCard here, no, so that you can learn it very easily, right. So here torque is equals to force. Force how much? No, Q times of your E into perpendicular distance. What is the perpendicular distance between them? No, therefore this is making an angle theta here, no, this is nothing but a 2L. So therefore this is your perpendicular distance, no. So what you will get it now, therefore here, so right, perpendicular distance, no, therefore here, so what is the perpendicular distance between these two forces? No, this is your perpendicular distance, no, this is nothing but a 2L sin theta. Clear? Clear? Right. So perpendicular distance between the two forces, no, is nothing but a 2L sin theta. So what you can write it now, torque is equals to E, therefore 2L, therefore you can write in 2L into Q. So therefore it is nothing but a P into E into sin theta. What is the direction of the torque? No, torque is in this direction, no. So this side it will be the F. So therefore this side it will be your, this is your dipole moment, no. Dipole moment is like this, it is no. Therefore here this is your dipole moment, you can see it now. This is your dipole moment. So this side it will be your electric field. So therefore it is inside. Therefore P cross E you can write down. Torque is equals to P cross E. So therefore in a vector form, no, you can rewrite it as like this. This is the torque acting on a dipole onto this. Clear? So when the torque will be maximum here, no, so torque will be maximum. So therefore when the torque is like this, no, so therefore what you can write it now, so here torque P cross E means what you can write it now, torque is perpendicular to this one, no, see we already know it, no, this is P, so this is E compulsory, therefore it will be the torque. Therefore so P cross E is nothing but like this, that means this torque will be perpendicular to E, torque will be perpendicular to P. Therefore so torque is perpendicular to P means torque dot P it will be equal to 0 and torque dot E it will be equal to 0. Most of the times this question is asked in the examinations, no, so please check it out onto this. Clear? So when the torque will be maximum, no, maximum torque, no, so it is nothing but a P into E. So this is your maximum torque when sin theta is equals to 1, that implies theta is equals to so 90 degree. That means so here if the dipole it is exactly perpendicular to the electric field, that means this is your electric field. How the dipole will be there? So dipole will be like this. This is your minus Q, this is your plus Q. Clear? So this should be a perpendicular, then torque will be the maximum onto this. Clear? Now when the torque will be 0, no, torque will be 0. So torque will be 0, therefore here sin theta is equals 0, therefore theta is equals 0 or 180. Therefore there is no torque will be acting onto this one, no. So if there is a dipole is kept, therefore in the direction of your electric field, no. Therefore here, so this is your positive, negative, no, therefore here it is negative, so this side it is positive. Therefore this is your dipole moment, this side it will be your electric field. Therefore if they are acting, no, this side it is going to experience a force, no, this side it is going to experience a force, no, net elongation it will be takes place onto this. So therefore what will happen now? Torque will be 0 in this. Clear? So this is the torque experienced by the dipole in a uniform electric field. Clear? So in a uniform electric field. Clear? So suppose there is a non-uniform electric field, what will happen now? Let us see. So suppose there is a non-uniform electric field, non-uniform electric field now. Clear? So non-uniform electric field means what? It is like this. Suppose here, no. What is this field now? This field is nothing but a diverging field. Diverging field means what? So here and here. So at A, electric field at A is greater than electric field at B. So non-uniform electric field. Electric field is not uniform here now. So what you can get it now? Therefore here this side is positive, this side negative. So here you can take it as minus Q. So therefore here it will be the plus Q. If it is like this, what will happen now? It is going to experience a force here, no? Therefore, here this side it is going to experience force. F is equals to, so therefore F at B, it will be equal to Q into EB. And this side it is going to experience a force, no? F is equals at A, it is Q into EA. So this is your force onto this one now. Clear? So this force is more, this force is less. So therefore force on A is greater than force due to the B. So what will happen now? This dipole, it will be able to rotate and it will be able to move. That means it will be able to rotate and it will be able to move. That means because this side force is there now. So the dipole will go toward this side now. Therefore, so here net force is not equal to 0. Net force is not equal to 0. Therefore, dipole will undergo like a translatory motion. Clear? And net torque also will not be equal to 0. So net torque also will not be equal to 0. So therefore, they will undergo like a rotational motion. Therefore, if a dipole is kept in a non-uniform electric field, so definitely, therefore, what will happen now? So there will be a translatory motion will be there and rotational motion will be there. That means here dipole is there now. What will happen now? It will be able to rotate and it will be able to move toward the heavier or stronger electric field region after this. Clear? Understand? No? So what will be the net force acting on this one now? What you can write it now? So net force here you can rewrite it as force, it will be equal to, so force A minus, that is force B. So what you can write it now? Q into E at A minus E at B. This is your net force onto this, right? So there will be one more formula is also is there. So that also we'll discuss now, right? In this way, if you know the electric field regions, no, you can calculate it now. Clear? And also we'll see, so different other formula is also is there to calculate the force experienced by the dipole in a non-uniform electric field. Clear? So this is one important concept, no? So related to the torque experienced by the dipole, no? Now we'll see one more concept now. So work done in rotating a dipole. Therefore, here work done in rotating a dipole. Right. So now let us see, there is a uniform electric field, we will take it now very easily first of all. So here a uniform electric field you are going to take it now. Later on we go for non-uniform electric field. Here there is a one dipole is there. This side is positive and negative. So this is your minus Q. So therefore it will be the plus Q. Here it is making an angle, suppose theta 1. Clear? So what I will do now, therefore we want to make it to rotate like this. That means this dipole will comes to here plus Q. So therefore it will be the minus Q here now. Therefore it is making an angle some theta 2. Clear? So what happened now? We are going to rotate here now. Therefore here, okay. So like this we are going to rotate it now. So therefore now here what will be the work done now? Here rotational work is done onto this one now. So work done, it will be equal to integral tau into d theta. Clear? So therefore from what is the torque now? Therefore Pe into sin theta. So integral therefore d theta from theta 1 to theta 2. Clear? So Pe is constant now. Dipole moment is constant. Electric field is also uniform. Integral sin theta is nothing but a minus cos theta. So theta 1 to theta 2. Therefore minus theta 2 minus or minus plus theta 2. So Pe of cos theta 1 minus cos theta 2. So this is your amount of work done in rotating a dipole from one angle to another angle. Clear? Clear? So now what is the work done now? Work done is nothing but a Pe into cos of theta 1 minus cos of theta 2. Clear? So therefore how much amount of potential energy is there now? How much amount of potential energy is associated with this one now? Therefore we can take it as one reference point now. Therefore when theta is equals to theta 1 is equals to 90 degree. So at that point potential will be 0, right? Why? Because cos 90 will be 0, cos theta 1 it will be equal to, that is 0. Therefore this is taken as like a where potential energy will be 0 now, reference point. So then how much amount of potential energy is associated? No, so you can take it as like a theta 1 equals 0. So PE therefore minus cos theta. Clear? This theta 1 equals 0, therefore PE cos theta. So U is equals to, therefore you can write it as minus P dot E. So this is your potential energy associated with the dipole. What is the potential energy associated with the dipole? No, minus P dot E. Clear? Now we will see, therefore here one very important concept now we are going to discuss now. So very important now. Therefore when the potential energy is maximum, potential energy is maximum, when it will be the maximum, therefore plus PE. So when it will be this one now, cos theta, it will be equal to minus 1. Why? So minus 1 means it is like this. Clear? So when it will be there now, theta is equals to therefore 180 degree now. Clear? So how much it will be? How should be there now? So potential energy is maximum now. Therefore let us see here now. So here there is a uniform electric field is there. So when the potential energy was maximum, therefore here is a dipole is there. Where is the dipole now? So it should be 180 degree. That means this side is positive, negative. Therefore it should be in the opposite direction. Means what? Here it should be the negative and here it should be the positive. So this side it will be your dipole moment, no? This side it will be your electric field, right? So dipole moment is toward this side, electric field is toward this side. Therefore what will happen now? So here, therefore here it will be like this, no? Potential energy will be equal to maximum. Now slightly if you disturb it now, therefore what will happen now? Slightly this is moved here, no? Moved here, no? What will happen now? When slightly moved, so due to this repulsion, repulsion, no? Therefore it will be able to undergo in this rotation onto this one. Therefore again it will never return back onto this. Here what is the force acting on this one now? Therefore net force it will be equal to 0 here, no? Net force it will be equal to 0. This is under equilibrium. But once it is disturbed, it will never return back to this one now. Therefore that is said to be like a unstable equilibrium. So this is the condition for unstable equilibrium, right? So remember that unstable equilibrium or stable equilibrium, one point you can remember, where potential energy is maximum, that is said to be unstable equilibrium. Where potential energy is minimum, that is said to be stable equilibrium. This point you remember always. So where potential energy is maximum, that is said to be unstable. So where potential energy is minimum, that is said to be stable. Now potential energy, when it will be the minimum now, minimum potential energy, it will be equal to minus PE. So therefore here what you will get it now? Cos theta should be equal to 1. That implies theta is equals to 0 degree. Clear? So 0 degree means what? Here it is minimum, no? Therefore this is said to be, just now I said no, it will undergo. However it is in the uniform, therefore it will be F is equals to 0 total force, and also it is said to be like a stable equilibrium. Clear? So here we can rewrite it as, this is your electric field here now, electric field, this side is positive, negative. Clear? So therefore here it will be the stable equilibrium, theta is equal to 0 means, so this side it is minus q, so this side it will be the plus q. Clear? So this is your dipole moment now, this side it will be your electric field, both are in the same direction. Now what will happen now? Now force is 0. So slightly if you replace it now, therefore slightly if you shift it here now, what will happen now? Because of due to this side force, no, attraction force, this side force, no, if you slightly disturb it like this, again come back to this one, no. If you slightly again disturb it, no, again it will come back to the same point onto this. So due to this reason, no, so therefore it will be remain stable like this only. So that's why it is said to be like a stable equilibrium. Clear? So these are the general concepts, no, related to the dipole, equilibrium, stable equilibrium, potential energy, and all this one, no. So we can rewrite it, right? So now let us see some questions onto this one, no. Suppose there is a one question here, no. Suppose here two charges are there, so 10 microcoulomb. So these are kept along the z axis. Therefore here okay, so this is placed plus 10 what you can write it, no, plus 10 microcoulomb, no, this is kept at so 0 comma 2 comma 2 centimeter comma 0, so minus 10 microcoulomb, no, therefore this is kept at 0 comma minus 2 centimeter comma 0, clear, right? So and in this one, no, electric field is there, no, I cap plus 2j minus 3k cap, therefore we want to calculate the torque and potential energy. Torque and potential energy. First of all, you have to calculate what is the dipole moment here, no. So dipole moment here, it is along the y-axis, it is given, no. So y-axis means what? Here it will be the minus 2, therefore minus 10 microcoulomb. So here it will be the minus 2, here it is a plus 2, so 10 microcoulomb, clear. So what will be the dipole moment here now? Dipole moment is in this direction now, so that is along the y-axis. So what is the dipole moment here now? Therefore charge is how much now? 10 microcoulomb, 10 to 10 to the power of minus 6. What is the distance between them now? Distance between this is nothing but 2 and 2, 4, because from here to here 2, here to here 2, 4 into 10 to the power of minus 2, therefore j cap. This is your dipole moment. How much now? 4 into 10 to the power of minus 7 j cap. This is your dipole moment, clear? Clear? So we want to calculate torque. Torque is nothing but P cross E, so I, J, K, dipole moment, no, 0, therefore it is 4 into 10 to the power of minus 7, so it is also 0. E, how much, no, 1, 2, minus 3. So here you can write it now, therefore here it will be equal to I taken now, this is, so minus 12 into 10 to the power of minus 7, this side is 0, so this is j, this is 0, this is 0, k plus k plus k, so this is AD minus BC, minus 4 into 10 to the power of minus 7, clear. So how much it will be now? Therefore minus 4 into 10 to the power of minus 7. So what you can write now? 3I plus k cap, 3I cap plus k cap will be your torque, clear. So this is the torque which is acting on a dipole, clear. What will be the potential energy associated with this one now? Potential energy, what you can write it now? Potential energy U is equals to minus P dot E. P is how much now? We got it as 4 into 10 to the power of minus 7 j cap dot I plus 2j minus 3k, electric field. So I dot j 0, j dot k, j dot j only we have to take it now. 4 into 2, therefore minus, actually minus 4 into 2, therefore 8 into 10 to the power of minus 7 joules. This is your potential energy associated with the dipole, clear? Right. So now we'll see one more question, no? So W is the work done, right? So W is the work done to rotate it from so stable equilibrium to, so theta is equals to 60 degree, from stable equilibrium to so 60 degree. So what is the torque to be acted at this point now? What should be the torque should be acting at this final point onto this, clear? So what is the work done now? Work done to stable equilibrium. Stable equilibrium means what? Theta is equals to 0 degree, right? So work done, it will be equal to how much now? Minus, that is nothing but P into E, so cos 0 minus cos 60, clear? So PE cos 0 is nothing but 1 minus cos 60 how much now? 1 by 2, therefore so 1 by 2 P into E, so this is your work done onto this, clear? So we want to calculate how much amount of torque should act at this position now. Torque, what is the formula for torque now? P into E into sin 60. Sin 60 how much now? So P into E is nothing but 2W, therefore PE is nothing but 2W, so therefore 2W into root 3 by 2, so therefore root 3 W. This much amount of torque should act at an angle of 60 degree. Like this, some simple application questions you can able to expect it in this one now. Clear? Right? We'll discuss one more concept now. Force acting on a dipole or force between the dipoles when it is kept in a non-uniform electric field. I told you I'll discuss this one now. So, in non-uniform electric field, force, conservative force formula, it already. So, force, what is the formula? Minus dou u by dou r, right? So, potential energy, what is the formula now? U is equals to minus Pe cos theta. So, substitute it now, therefore, F is equals to minus of minus plus. Dipole moment we are not going to change onto this one now, P and theta, therefore, cos theta into dE by dr or dou E by dou r. So, this it will be your force acting on a dipole due to non-uniform electric field. Here dE by dr is nothing but electric field is changing with respect to the distance here now. So, if you want to write down in terms of dot product now, therefore, F so is equals to therefore P dot, right. So, here you can write it based on this angle onto this, clear. So, F is equals to P into cos theta into dE by dr, right. Let us see one important concept now. What will be the force acting between the two dipoles? Very, very important concept now. Suppose there are two dipoles are there. Let us take one like a question here now. So, question, there is a one dipole is there. This is lying in the same axis onto this. Let us take therefore, here there is a one dipole is there, short dipole P1 no, and another one more dipole is there. Therefore, it will be the P2 dipole moment. So, the distance between the centers no, it is given as like a r, clear. So, this is nothing but a dipole interaction onto this, right. So, we want to calculate what will be the force acting on the second dipole due to the first dipole. See, what is the force acting on the second dipole now? How to calculate it now? Force acting on the second dipole, it will be equal to this dipole moment P2 cos 0, right. So, therefore, what will happen now? Here cos 0, now this is the dipole and this is creating the electric field at this point. That means, this P1 is creating the electric field. That means, so electric field due to therefore d by dr, electric field due to this P1. How much now? K into P1 by r cube, axial line no 2, clear. So, therefore, you can rewrite it as cos 0 is 1 no, therefore, 2k into P1 P2 into differentiation of this one no, therefore, differentiation of r cube means, so minus 3, right, into r to the power of minus 3 minus 1, clear. So, what you will get it now? Minus 6 k P1 P2 divided by r to the power of 4. This is your force, clear. So, this side is negative, positive, negative and positive. Therefore, here this is negative, positive, therefore negative, positive. Therefore, attraction force it will be there now. Attraction, correct. So, that is why it is said to be like a negative onto this. Here force between the two dipoles now is inversely proportional to the r power 4. Very, very important now, right. Force due to these two dipoles no, it is inversely proportional to the r to the power of 4. So, force between the 2 point charges is how much no? 2 point charges. So, what you can write it now? Force between charges no, it is inversely proportional to the square of the distance. Here charge and dipole, we will do this one now, okay. So, it is inversely proportional to the cube of the distance. Here dipole and dipole force is inversely proportional to the r to the power of 4 now. Very, very important concept now. So, be careful on this point, right. Force between the 2 point charges is inversely proportional to the square of the distance. Force between the dipole and charge is nothing but r cube. Force between the dipole and dipole is nothing but r to the power of 4. I said I will do this question no. So, now, so we will see there is a one dipole is there now. Let us see this one now. There is a one dipole is there, minus q and therefore, it will be the plus q. So, therefore, we want to calculate that some charge is there now, therefore, at certain distance. So Q is the charge is there. So what is the dipole moment here now? Dipole moment is like this. What will be the electric field along the equatorial line now? Electric field is in this direction now. Clear? So electric field, so therefore force acting on this one is how much now? So electric field into Q, correct? Electric field due to this dipole is how much now? Electric field now. So K into P into Q by therefore RQ. This is the force acting on the charge. So this is the force acting on the charge now. That much amount of force is acting on the dipole now. Therefore, like a Newton's laws now, action and reaction now. This is the force acting on the charge. The same amount of force is acting on the dipole. So therefore, force acting on the dipole is inversely proportional to RQ. Just now I said no. So force between the dipole and charge is nothing but inversely proportional to RQ. Clear? So in this way, for non-uniform electric field also, therefore you can calculate it no by using this formula. F is equals to minus, therefore that is dou U by therefore dou R. So you can use potential energy is nothing but minus P dot E. Clear? So you can, so this is a force acting on this one. Clear? So in this way you can calculate the force between the two dipoles and charges now. Let us see one more question now. Suppose there is a one dipole is there no, dipole moment is, therefore there is a one electric field is there, electric field. So here one dipole is there no, one dipole, therefore this side positive negative no, this side is negative and this side is positive, correct. So therefore what I am going to do now, I am going to disturb this one like this, minus Q, therefore this side is plus Q and this is plus Q. Therefore what I will do now, this dipole is there, I will just slightly disturb it now, I will release it. What will happen now, this dipole now, it will be able to oscillate like this. So we want to calculate the time period of this one now. What is the time period now? How to calculate? Time period means simple harmonic motion. Simple harmonic motion means what you have to write it now? Acceleration should be equal to minus omega square into x. Here which acceleration will be there? Along the angle theta is changing now. Angular acceleration is equals to minus omega square into theta. So we can rewrite it as torque. Torque is nothing but a P into E into sin theta. This provided that theta is very very smaller no. Torque is equals to, therefore what you can write it now, I into alpha, and this is restoring torque no, minus you can write down theta is small. If theta is small, so therefore sin theta is nearly equal to the theta. Therefore what you can write it now, alpha is equals to minus therefore PE by moment of inertia into theta. Clear? So therefore by comparing this one now, therefore omega square is equals to PE by moment of inertia. So therefore here omega square, omega is equals to root of PE by I. So this is nothing but a 2 pi by T. So T is equals to therefore 2 pi into square root of I by PE. This is your time period of a dipole if it is oscillating in a uniform electric field. Right. So like this you can solve so many different combination questions no. So right. So you be thorough onto this one no. So we can have, sometimes they will give the mass of this one no. You can calculate the moment of inertia. How to calculate the moment of inertia I already explained in rotational motion no. So please go through that moment of inertia also. So they may ask you moment of inertia combination so many times no, you can expect the questions, right. So more than this one no, therefore for NEET level and JEE mains level no, you cannot expect it no. Some more difficulty level questions no can be done in the IIT-Advance after this, right. So if any time permits no, therefore we'll see some more difficulty level questions related to the dipole which is asked in the IIT-Advance now, right. So that we will discuss now. So please thank you for watching. Please subscribe to my channel now and follow my channel so that you can learn the physics very easily, which will be helpful for NEET, IIT-JEE-ADVANCE. So any teacher trainings onto this one now, right. So you can learn the physics very easily, even which will be helpful for your board also, right. Thank you.